Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 2. Linear and Polynomial Regression. Least squares regression to polynomials is used to find the best-fitting polynomial to a set of data points. This method minimizes the sum of the squared differences between the observed data points and the values predicted by the polynomial. Polynomial regression is a versatile tool used across many scientific and engineering disciplines due to its ability to model complex relationships between variables, make predictions, and optimize processes. In many physical systems, where relationships between variables are not linear, polynomial regression can be used to approximate these relationships. It is commonly applied to fit experimental data from experiments. One of the most common models in curve fitting is the polynomial model, where a set of discrete data is approximated by an nth-degree polynomial. Among polynomial models, the linear model, case of n equals 1, is a model encountered in almost every field of science and engineering. For the polynomial model, the objective function leads to the following equation, where xi denotes the set of measured or observed data. A0 through am are the coefficients of the polynomial and are commonly referred to as model parameters. The objective function is a single equation with m plus 1 unknowns. We derive m plus 1 equations by differentiating e with respect to the model parameters and then setting each equation to 0 as follows. The collection of these equations altogether forms a system of linear equations, which is expressed in matrix form as follows. Looking at this generalized equation, we can easily extract a system of equations for low-order polynomial models. For example, for a linear model, we extract the first 2 columns and 2 rows of the coefficient matrix. For a quadratic model, we copy the first 3 columns and 3 rows of the coefficient matrix and the corresponding right-hand side elements. The resulting system of linear equations for m equals 1, 2, or 3 can be solved by Cramer's rule. For high-degree polynomial models, the linear system tends to be ill-conditioned. In many cases, the degree of a polynomial is severely restricted due to rounding errors. The polynomial models of m greater than 7 generally produce absurd results using single precision arithmetic. It is recommended to use direct solution algorithms with pivoting and high-precision arithmetic to overcome the adverse effects of ill-conditioning. Also see sections 2.7 and 3.5. A series of experiments are conducted to determine the latent heat of evaporation of an aqueous solution as a function of temperature. Use the experimental results provided below to find a linear relationship and analyze the best fit results. We tabulate the given data in columns. Replacing x and y with t and delta h respectively, we obtain the linear model and the system of linear equations for the model parameters as follows. Notice that, to solve this system of equations for a0 and a1, we need to first obtain the numerical values of the system, which require summation of all the temperatures, temperature squares, enthalpies, and the product of enthalpy temperatures. If you are using a worksheet, it can be very handy to do such calculations and summations. Squares of the temperature, as well as the enthalpy temperature products, are calculated and tabulated. The column sums give the quantities we seek. Next, substituting these values into the linear system and solving it gives a0 and a1 as 36.1586 and minus 0.08406, respectively. To estimate the sum of the squares of the mean deviation, we need the arithmetic average of the enthalpies, which is found as 32.46. We now can calculate the mean deviations in the fourth column. The column sum gives the sum of the squares of the mean deviation. Next, we calculate the residuals and place them in the fifth column. The column sum gives the sum of the squares of the residual. Using these quantities, we can calculate the r-squared, which turns out to be 0.93577. Plotting the data and the best fit line, we observe that the line agrees very well with the data. To better analyze the agreement, we plot the residuals. Recall that the magnitude of the average enthalpy was 32.46. The relative magnitude of the residuals with respect to the mean value of the enthalpies in the first and second data points is about 3 and 4%, respectively, which is not bad. Next, we create a PO plot, which is a graphical tool to analyze the performance of a regression model by comparing the predicted values to the observed or actual values. Note that the predicted values are placed on the horizontal axis and the observed values on the vertical axis. If the regression model is perfect, all the points should lie exactly on a 45-degree line, where the predicted values match the observed values. Deviations from this line indicate differences between the predicted and actual values, highlighting how well the model is capturing the data. When we apply linear regression to the predicted observed data, the slope and the intercept of the line are 1.18 after 5 zeros and minus 1.8 times 10 to the minus 5, respectively. This would be considered ideal. Moreover, note that the r-squared value reported here is identical to that of the previous linear regression. However, in nonlinear models, the r-squared values of the PO lines are different. If we were to observe a consistent pattern where predicted values are systematically higher or lower than observed values, it would indicate a bias in the model. Identifying such biases can suggest where the model might need improvement or recalibration. In this example problem, we do not observe any bias, so we can conclude that the linear model is suitable for the regression analysis of the given data. The average confidence interval can be determined once the RMSE is calculated. The 68% confidence interval and 95% confidence intervals are depicted on the figure. When using a polynomial model, it is tempting to increase the degree of the polynomial to improve the model and its prediction ability. As the degree polynomial, assuming the number of data points is sufficient, is gradually increased, the residuals decrease and r-squared improves until the observed and predicted data become identical, i.e., r-squared goes to 1. If the data is corrupted by significant noise, the noise is also included in the fitted high-degree polynomial model. Overfitted polynomials depict large oscillations leading to abnormal deviations for values other than the corresponding data points. Let us visually explore the effects of increasing the degree of a regression polynomial for a given dataset. When the data is fitted to a line, the r-squared is about 0.96. The agreement of the line and the data is fairly good. For a quadratic polynomial, r-squared improves. Similarly, for third and fourth degree polynomial models, the r-squared values continue to improve. The best fit curve depicts good agreements with a few outliers. For the fifth and sixth degree polynomial models, we achieve higher r-squared values, but the polynomial starts to depict oscillating behavior like the Runge's phenomenon. The linear systems resulting from implementing polynomial regression models can be ill-conditioned, and the round-off errors also tend to distort the solution. Polynomials up to the third or fourth degree can be managed relatively without a problem. However, polynomial models of degrees higher than 4 are rarely used. With this note, we conclude this video session. That is all for now. See you next time with another topic. Bye.